Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Marianne Freiberger.
And I'm Rachel Thomas. My good friend Ash asked me recently, what is infinity plus 100? And what is infinity plus infinity? Now, they are good questions, Ash. And as I said to him, there is actually different types of infinity. They're all pretty weird. And many mathematicians and physicists are still thinking hard about whether they even exist. Now, Ash's question reminded us of everyone's favourite mathematical hotel, Hilbert's Hotel.
Yeah, and the idea goes back to the German mathematician David Hilbert, who used the example of a hotel to demonstrate the counterintuitive games that you can play with infinity. So suppose that your hotel has infinitely many rooms, numbered 1, 2, 3, 4, 5, 6, 7, etc. And imagine that all the rooms are occupied. And then a new guest arrives and asks to be put up. What do? Well, it's easy. Ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, the guest in room 3 to move to room 4, and so on. If there were only finitely many rooms, then the guest in the last room would have nowhere to go. But since there's infinitely many, everybody will find a new place to stay. You'll have to ask the guests to move simultaneously, though, because if you ask them to move one after the other, the move might take an infinite amount of time, since infinitely many guests have to move. You can also make this work if you had 100 new guests arriving, because then you just ask the first guest to move to room 101, the second guest to move to room 102, and the third to move to room 103, etc. So in answer to Ash's question, infinity plus 1 is still infinity, and infinity plus 100 is still infinity.
Now, what about Ash's second question? Suppose an infinite number of new guests arrive, forming an orderly queue outside. In this case, we ask each existing guest to move into the room whose number is 2 times the number of their current room. So the guest staying in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so on. After this manoeuvre, only the even-numbered rooms are now occupied, the rooms 2, 4, 6, 8, and so on. The odd-numbered rooms are now all free, so you can put your first guest into room 1, the second new guest into the next odd number, room 3, the third new guest into room 5, and so on. And everybody is happy. So, Ash, the answer to your second question is infinity plus infinity is still infinity.
But technically, we've been talking about a very specific type of infinity. It's the infinity that you find in an infinite list, and it's called a countable infinity, because if you had an infinite amount of time, you could just count it. But there are other types of infinity too. One of our favorite people to ask these sorts of questions was our late boss, John Barrow. We asked him the question, does infinity exist, in 2012 as part of our science fiction science fact project, where Plus readers got to vote on which questions we should ask the experts. Here's John's excellent answer to that question.
Well, this is a surprisingly ancient question, and the famous and clever distinction that was introduced to try and make sense of it was made first by Aristotle, who distinguished between 2 varieties of infinity, one which he called a potential infinity. And so this would be the type of infinity that would characterize an unending universe, or characterizes the list of ordinary numbers, 1, 2, 3, 4, 5, and so on, forever. So these are lists, or they are expanses, which have no end. They have no boundary. But you can never reach the end of the list of all numbers by listing them, or by going on a spaceship in a flat space and carrying on. So these are lists, they are volumes, they are areas, they are lengths, which have no bound. And these are what Aristotle called potential infinities. And he was quite happy about them. He recognized them as existing, and they didn't create any grand scandal in his way of thinking about the universe. But he distinguished them from what he called actual infinities. And actual infinities he banned, and he said that they couldn't exist. So actual infinities would be something that you could measure, something local, like the density of something, or the brightness of a light, or the temperature of something that was hot, becoming infinite. So this was something that you would encounter, or you could encounter, locally in the universe. And this belief was bound up with his other belief that there couldn't be a perfect vacuum, because if there could, he believed that you'll be able to push something and accelerate it, and it would go to infinite speed because there was no resistance to it. So this was the ancient distinction between actual infinities and potential infinities. And for many thousands of years, Aristotle's philosophy was bound up with Western Christian dogma and belief about the nature of the universe, and his distinctions remained. People thought that there couldn't be actual infinities. In fact, the only infinity was supposed to be the divine, God, but there could not be any created within the universe by anything that we did.
But as John told us, when you look at infinity in a mathematical way, strange things can happen.
Things changed in the world of mathematics at the end of the 19th century when Georg Cantor in particular, developed a more subtle way of looking at mathematical infinities and distinguishing one type of infinity from another. So he recognized that there was a very simple, smallest type of infinity, which was that 1, 2, 3, 4, 5 unending list. And he called that a countable infinity. And any other infinity which could be counted in this way, just by putting its members in one-to-one correspondence with the list 1, 2, 3, 4, 5, and so on, was also called a countable infinity. This got some funny consequences. For example, the list of all the even numbers is also a countable infinity. Intuitively, you think there's only half as many even numbers as ordinary numbers. That would be true if the list was finite. But when the list becomes unending, it's not true, because you can draw a line from 1 to 2, and from 2 to 4, and from 3 to 6, and so on forever. And every even number will be joined to one and only one number in the other list. So there are as many numbers in one list as there are in the other. This was first noticed by Galileo, who thought it was so strange that it put him off thinking about infinite collections of things any further. So he thought there was just something paradoxical about it. But Cantor then went on to show that there are other types of infinity that are in some sense infinitely larger, which could not be put in one-to-one correspondence with the ordinary numbers. And that infinity is characterized, for example, by the list of all the numbers with unending decimal expansions, so what we call the real numbers. So they cannot be counted, so there's no recipe for listing them systematically. Whereas for the even numbers, we saw there was, and for all the rational numbers, all the rational fractions there is. So if you have 2 over 3, 3 over 4, and so forth, the way you list those is you just add the numerator and the denominator. You add all the ones where it adds up to 2, then all the ones where it adds up to 3, and all the ones where it adds up to 4. And that is an infallible recipe for counting all the rational numbers, and you won't miss any. So they're countable as well, even though in some intuitive sense there seem to be lots more of them. But if you count them in the right way, there's just the same number. So this led people to think again, really, about the status of infinities. Cantor was treating infinities not just as potential infinities, but as actual infinities mathematically. You could add them together. So a countable infinity plus another countable infinity was a countable infinity, and so on. And there was a great fuss in the world of mathematics whether this should be allowed. So some mathematicians thought that by allowing Cantor's transfinite quantities, as they were called, into mathematics, you were introducing some type of subtle contradiction somewhere. And as you know, if you introduce a contradiction into a logical system, then eventually you'll be able to prove anything is true. So it would create the downfall of the whole system. So this development in pure mathematics, which was eventually accepted and forms its own sub-branch of mathematics today, led some theologians even and philosophers to rethink their ancient attitude about infinities. So they could see that if you're a theologian, you didn't have to regard the appearance of mathematical infinities as some sort of challenge to the notion that the divine is the only infinity, because there were quite different varieties of infinity. And in fact, Cantor went on to show that finding this infinitely bigger set of the real numbers wasn't the end of the story, that you could find infinitely bigger sets still, and so on, all the way upwards forever. And there was no biggest possible infinite collection of things. If someone presented you with one, you could create a bigger one that wasn't in one-to-one correspondence with it, just by finding the collection of all the possible subsets of that infinite set. So this never-ending tower of infinities then had something that was just called absolute infinity, sort of unreachable summit of the tower.
Now, Cantor's results on infinity were indeed controversial, so much so that the mathematician Leopold Kronecker is reported to having called Cantor a scientific charlatan, a renegade, and a corrupter of youth. And that's just for mathematical infinities. So how about physical infinities?
But physical infinities have since, I think, in modern physics really become rather separate from the study of infinities in mathematics.
So what physical infinities are there? What would be an example?
Well, a classic example is if you find solutions of Einstein's equations which describe expanding universes.
So solutions of Einstein's equations are possible universes.
Yes. So if you trace them backwards in time, they appear to begin at a point in the finite past where the density was infinite.
So our own Big Bang is like that?
If we had a Big Bang in the past, then there are solutions which suggest it had an infinite density in the past. If we look at the centre of a black hole, there might be many black holes in our galaxy and nearby, suggests that if you fell in, perhaps you encounter an infinite density at the centre. So these are unusual examples because they are actual infinities, okay? We're happy to think of the universe being infinite in size, perhaps infinite in future age. These are potential infinities, and they don't seem very threatening. But there are other places in ordinary physics where infinities sometimes arise. If you study aerodynamics or fluid mechanics, you might have a wave becoming very, very steep and nonlinear and then forming a shock. And if you have simple equations describing the shock wave formation, some things may become infinite.
But is that just the equations becoming infinite
Yeah.
because they fail to describe reality at that?
Yes,
divergent
indeed.
level?
So when this happens, your first reaction is, oh, this is a failure of our model. Okay, and so what we do is that we add some of the friction of the air in, some of the viscosity, and instead of having an infinitely steep change in the velocity gradient, it becomes finite, still very steep, but the viscosity just smooths over the infinity. And in most areas of science, if you see an infinity, this is what it suggests to people. In particle physics, there was a much longer standing, more subtle problem that for many, many decades, the best working theory in particle physics, quantum electrodynamics, which is still the very best theory in the whole of science, its predictions are more accurate than anything else that we know about the universe in any respect. Yet, the only way you could extract those calculations, those predictions, was to deal with a very awkward problem, that when you did a calculation about what you should observe in an experiment, you always seem to get an infinite answer with an extra finite bit added on. If you then subtracted off the infinities, the finite part that you were left was the prediction you expected to see in the lab. And this always matched the experiment fantastically accurately. So this process of removing the infinities was called renormalization. Many famous physicists found this deeply unsatisfactory, and it must just be a first version of a theory that could be improved. We were not looking at it in the right way. And the great excitement about string theory in the 1980s, why it suddenly became investigated by huge numbers of physicists, was because for the first time particle physicists found a finite theory. So a theory that didn't have these infinities popping up.
Yes, Rachel, do you remember when we had to learn about all those infinities in quantum electrodynamics?
Yes, I do. We were very lucky to have some private lessons in Cambridge from our lovely friends Jeremy Butterfield and Nazim Bhutta. And then we went on a little tour of the United States to meet some of the great minds behind quantum electrodynamics and the wider framework quantum field theory. And this included the chance to interview the legendary Freeman Dyson, who is one of the loveliest people we've ever interviewed. Dyson did a lot of work to help sort out those pesky infinities in quantum electrodynamics.
And it's just so weird that this procedure of renormalization that John talked about, where you basically subtract infinities of an infinite answer to get a finite answer, which then actually matches experiments. It's so weird that this actually works. And I remember we drank quite a lot of gin in hotel bars to get our heads around this. Now, if you, the listener, would like to find out more about this project and what we wrote as a result, go to plus.maths.org and search for Taming QED.
So we've had mathematical infinities and infinities that show our physical theories are not quite right. But as John told us, there's something else potentially lurking in the universe.
The next and other type of infinity that we've just mentioned are the ones that you get in gravitation theory and in cosmology. And people sometimes have a different attitude to those. Particle physicists always thought that their infinities are just a sign that you hadn't got the best theory yet, so you have to work harder. In cosmology, there's a difference of opinion. So there's some people who think like that, and who think that if we keep searching for a theory of quantum gravity, which might turn out to be a version of string theory, then that theory won't have the infinite density at the beginning of the universe, the infinite temperature, that we call the Big Bang. But there are other people, Roger Penrose is one, for example, who thinks that that initial singularity at the beginning of the universe plays a very important role in the structure of physics. And you can see it's very special. It's not like the infinities in the shock waves or in electrons hitting one another. If you're going to have something special in the universe, then the beginning of the universe is about as special as it gets. You see, the way our universe is set up at the moment, there's a very curious defense mechanism. On a simple interpretation of things, there's an infinite density occurring at the centre of every black hole, where material falls in and in and in and in. And it's just like that infinity at the end of the universe. But when that happens in the universe, a black hole creates this horizon around that phenomena, and light cannot escape. So we are insulated. We cannot see what goes on at those places where the density looks as though it's going to be infinite, and nor can it influence us. So these horizons that occur in general relativity protect us from the consequences of places where the density might be infinite, and they stop us seeing what goes on there.
And we have no idea what goes on.
Well, there was one situation where we might see such a thing. Stephen Hawking, long ago in 1975, showed that black holes gradually evaporate their mass and energy, very, very slowly. That there's a quantum tunnelling process that particles can leave the black hole. And if a black hole is very small, about the mass of a mountain, then, and its size would be then pretty much just the size of a proton, then at the final moments when that explosion occurs, it will be like seeing a mini Big Bang occurring. And we can predict what we would see. Lots of gamma radiation with very high energies, 100 MeV gamma rays, lots of relativistic electrons and positrons, which, if the explosion occurred in our galaxy where there's a magnetic field, would spiral around and emit synchrotron radiation. Mm-hmm. So it's like a mini supernova explosion. So in cosmology, we have this slightly different attitude towards infinities.
And is that a conventional view? So would most cosmologists accept that these infinities exist, these actual infinities? Or is it
I think there's a fair division. I think probably cosmologists who come from particle physics, who are interested in string cosmology and what string theory has to say about the beginning of the universe, would all tend to the view that singularities are not real, that they're just an artifact. Even if they're an artifact and something happens to remove them, the density still becomes stupefyingly high before anything can happen to remove them. So it's still a very bizarre situation where you would have densities 10 to the power 96 times bigger than that of water. For all practical purposes, that seems like an infinite value.
That was the wonderful John Barrow talking to us back in 2012, answering our and your burning question, does infinity exist? You can read more on plus.maths.org/infinity. Thank you very much, Ash, for your question. Now, if anybody else has a burning question you'd like answered about maths, the universe and everything, why don't you email us at plus@maths.cam.ac.uk or contact us on Twitter via the handle @plusmathsorg.
That's all we've got time for in this podcast. The music on this podcast is from Ollie Freak and the track is called Experimental 5. You can find his music at soundcloud.com/OLIFREKE. Thanks for listening and bye for now.